Hello everyone, welcome to the webinar on the topic nuclear reactor types and their applications. So today I will be your moderator Anjuhan, and today we have three speakers, Katia and Zero from Obni's Institute for Nuclear Power Engineering and Linux from National Research Nuclear University, MIFI. So without any further delays, let's start our webinar. So the first speaker, Katia, will talk a few words on thermal nuclear reactors.
Good afternoon, guys. Hope you're all doing well. My name is Katia, as the moderator said. I'm studying for my bachelor's degree in nuclear physics and technology, and currently I'm in my third year at MIFI. So today I'll be explaining more about the thermal reactors. Next, please. So we'll see what a thermal reactor is and some of the types of thermal reactors and their mode of operation. So currently, the majority of nuclear power plants in the world are water moderated, and in other words, you can say they are thermal reactors. They are categorized as either light water or heavy water reactors. Light water reactors use purified natural water as the coolant or moderator, while heavy water reactors employ heavy water or deuterium oxide. So the first one I would like to explain about the pressurized water reactor. So this is the most common type of thermal reactor, and the design of the pressurized water reactor originated as a submarine power plant. So pressurized water reactor use ordinary water as both coolant and moderators. So you can ask yourself how it operates. The design is distinguished by having a primary cooling circuit which flows through the core of the reactor under very high pressure, and as a secondary circuit in which steam is generated to drive the turbine. In Russia, these are known as VVER types, water moderated and cooled. So here is a diagram of a pressurized water reactor. The second one is the boiling water reactor. This type of reactor has many similarities to the pressurized water reactor, except that there's only a single circuit in which the water is at low pressure so that it boils in the core at about 285 degrees Celsius. The reactor is designed to operate within 12 to 15% of the water in the top part of the core as steam, and hence with less moderating effect, and thus promote efficiency. So the boiling water reactor heat water and produce steam directly inside the reactor vessel. Then water is pumped up through the reactor core and heated by fission. Pipes then feed the steam directly to a turbine to produce electricity. The unused steam is then condensed back to water and reused in the heating process. So here you can see the boiling water reactor diagram. So the other one is the pressurized heavy water reactor. A pressurized heavy water reactor are in many ways similar to pressurized water reactors. It is a nuclear power reactor commonly used and using enriched natural uranium as its fuel that uses heavy water deuterium or deuterium oxide as its coolant and moderator. The heavy water coolant is kept under pressure, allowing it to be heated to higher temperatures without boiling, much as it's in a typical pressurized water reactor. The other one is an advanced gas-cooled reactor. These are second generation of British gas-cooled reactors using graphite as the neutron moderator and carbon dioxide as coolant. These tubes are then grouped together in graphite sleeves to form a fuel assembly. And an advanced gas-cooled reactor assembly is made of 36 steel tubes, each containing 64 pellets. Next, please. So you can ask yourself how the fuel used is produced. So enriched uranium hexafluoride arrives at Springfields and is converted to uranium dioxide powder in a kiln using a process called the integrated dry route. We then process the uranium oxide powder again, press it, heat it on a furnace, and grind it to produce the fuel pellets. The fuel pellets, which are about the size of timber, are stacked inside fuel tubes. Once the tubes are sealed and pressurized, they are put together in a graphite sleeve to form a gas cooled reactor fuel assembly. After it is thoroughly inspected to check the quality of the fuel, we pack it ready to send to the reactor, to LWDR reactor. Next, please. So I would like also to talk about the light water graphite moderated reactor. So the light water graphite reactor is like a combination of the advanced gas-cooled reactor and the heavy water reactor. The moderator is graphite, so the core is very similar to that of the advanced gas-cooled reactor, being made of graphite blocks with vertical holes of the fuel channels and control rods. The coolant is light water contained in pressure tubes, which also carry the fuel elements as a steam-generating heavy water reactor. So the steam is generated directly to the reactor core and separated from the water externally in steam drums. So yeah, this is what I can talk about the light water graphite moderated reactor. So here is a scheme where you can learn more about the light water moderated reactor. So thank you very much for joining us today. You can text me on my email or on my Telegram. Here is my handles. Thank you very much.
Thank you very much, Kritika. So the audience, do you have any questions? So if not, let's go to our second speaker, Lennox. He will be talking about SMR. Lennox, the floor is yours.
Thank you, Mr. Antron. Okay, good day, guys. It's a pleasure to have an audience. My name is Lennox Sigiti, and I'm going to take you through the strategic role of small modular reactors. So there are quite a revolution in the energy landscape. So we can hop in and start. So today we are going to talk about what are SMRs, their key design features, and also the scientific phenomena behind small modular reactors. So after that, we can talk about the challenges and opportunities and also future developments of small modular reactors. So to start, what are small modular reactors? So small modular reactors are nuclear reactors with power output typically between 10 to 300 mega electric watts, but they can go as far as 5 mega electric watts. And they are designed to be manufactured at a plant and brought to a site to be assembled. So the term small modular reactors comes from their size, their capacity, and also their modular construction. And when we depict this modular construction, we are looking at how can they be joined or assembled to build up a required electric capacity. So SMRs are typically not a distinct type of reactor, but rather a family different reactor designs. So they range from all these other reactor types which have been described, the pressurized water reactor, the generation 4 reactors, etc. So we have two very famous types of small modular reactors which have been in existence. Right now, we have the academic Lomonosov, which has been laid out there by Rosatom. In the offshores of Russia, they are powering up a city. Each small modular reactor has got a capacity of 35 megawatts electric, and they are having an output of around 64 megawatts electric, which is quite high. So this world's first floating nuclear power plant was commissioned in 2019. And also we have the one which has been developed by NuScale Power in the United States of America, which is an onshore working model. So this nuclear small modular reactor is called the Voyager. So it has been commissioned in 2022. So as you can see, small modular reactors are not a thing of like a new idea, but they've been in existence back before. They are just to be existing since the 1960s, but they've been only used in the nuclear propulsion. For example, in icebreakers, the ships, they were only used for nuclear propulsion, and their commercial aspect has not been realized until recent years. So we can take a look at how small modular reactors works. So how do the small modular reactors work? So as you can see by the graphic displayed here, they are compared to a human size. So that's how long and how tall a small modular reactor can be. But it's in comparison, right? Then we are saying, these small modular reactors, how do they work? Like what we said before, they also use the concept which are being used by other reactors, which is the concept of nuclear fission. So from nuclear fission, the heat generated through the splitting of an atom is used to heat water, and we get steam. Then this happens at the core of the reactor. Then we have control rods which control and regulate the heat in these chain reactions. So this steam is moved, it moves, it converts into the secondary loop, whereby it drives the turbines that generate electricity to the steam generation. Then whereby we say we transform our thermal energy to kinetic energy, then kinetic energy to electric energy. So this steam, after it has turned the turbines, it passes through what we call the reactor coolant pumps. So this regulates the reactor's coolant so that it does not overheat. And this reactor is kept under pressure by what we call a pressurizer. So in order to ensure that the water does not boil. Okay, so we can go to the next slide. So SMRs have been in deployment, some of them, and some of them have been at different stages. So some of them have been at design stages, some of them have been at prototyping. So in total, we have about, by 2022, we have about 98 reactors, 98 reactors in different stages. And at the moment, as you can see from the timelines, we have the academic Lomonosov, which has been commissioned in 2019 at the first part. Then we have our the Voyager, which had been commissioned in around 2021, 2022. So, which has been a prototype operation from them. So the developments are continuing going on, and there's been a focus that in the near future, more SMRs will be in the commercial operation stage as compared to existing nuclear power plants. So with developing timelines and technologies, we're going to realize more SMRs. So let's now talk about the key design features of small modular reactors and the scientific phenomena behind them. So these small modular reactors discuss the issues of, we already discussed the issue of their modularity, whereby we are saying once they are constructed at the factory in the industry, they're now transported to the site where they should be combined and build up. Like what's happening in the construction sector, we have Legos, which are used in the construction sector now. So it's now like we have our own energy Legos. We can build up to our required energy demand for be it a nation. So these, with their modularity, they can be stationed at different areas, like those remote areas, or in countries where a 1 gigawatt grid is not supported. So they've also a safety feature, which is a passive safety feature. It relies on natural physical phenomena such as gravity and convection. So these features, safety features, allows them, the small modular reactors regulation and licensing to be a bit lighter than the normal, or what we call the traditional nuclear energy reactors. And also, they have a fuel cycle which ensures that we have longer intervals between refueling and fueling. Also, now the scientific phenomena behind the SMRs have been discussed as nuclear fission. They are also known in the heat generation and thermal efficiency, whereby you can use them in heat industry, like what they were being used earlier as propulsions. So the heat generated is used to produce steam, which then drives turbines, as we have discussed. Okay, we can now hop on to the next slide. So we have different designs of SMRs, as I've articulated in the first slide, that there are different designs of SMRs around the world, and they take on the traditional concepts which have been there. And some research and innovations shows that SMRs could be the potential to unlock nuclear fusion. So now, as we can see, we have land-based water coolant reactors, which I've mentioned about the Voyager in the United States, and we have got the marine-based water coolant reactors, which we have the academic Lomonosov in Russia, and we have also microreactors which are being prototyped, which can range in the capacity of 1 to 10 megawatts electric. And we have the fast reactors and the high temperature gas-cooled reactors, which have been described by Katia. And we also have the molten salt reactors. Okay, next. Now, we need to discuss about the challenges, opportunities, and future developments around SMRs. Likewise, we know for every project, there are challenges, there are opportunities to its appraisal, and there are also future developments which we can look into. So for SMRs, they have innovative designs with good safety features. So these safety features allows them to be disseminated at an earlier stage in the nuclear commissioning. And also we have economic drivers. They are economic drivers in the case that they have a lower capital costs as compared to the traditional nuclear power plant, and they have the ability to match an energy demand because they can be combined in modularities. Imagine this case that we have maybe developed stage where we have developed 300 megawatt each for small modular reactor. Maybe then if we want to supply to a country maybe with a capacity of an energy demand of 1 gigawatt, we can even realize a nuclear power plant for all those countries which have not been able to realize nuclear power plants because of their capacity or their ability to match the regulation aspects of developing a nuclear power plant. And also there are market opportunities for small modular reactors now because of energy needs in remote areas, because of changes in climate change now and the growth in decarbonizing. So the challenges which are mainly faced in small modular reactors commissioning is the regulatory aspect. So the licensing and regulations are critical to the deployment of small modular reactors. This is the one which takes longer periods because there will be rigorous activities to ensure that these are safe for the environment and for the personnel working in them. So there are also future developments which have been in discussion, like the advanced materials, the nanomaterials which are being developed, and the ceramics, which are 3D ceramics. So these advanced materials are believed to withstand high temperatures and pressures and radiation levels, which are a great need in the SMRs to support their passive safety system. And there's also a discussion in the waste management, whereby we are saying nuclear small modular reactors have a comparable better waste output than the conventional nuclear reactors which are in place. So these types and volumes of nuclear waste produced by these SMRs are quite a place where one can venture into research and stuff. So thank you for listening. We would like to entertain your questions if you have any.
Thank you very much, Lennox, for your wonderful presentation. So, audience, do you have any questions? So if you don't have any questions right now, and if you want to ask at the end, yes, you're welcome.
Sure.
Okay, so let's move to the final part about the fast neutron reactors. Zero, it's your chance now.
All right, thank you, Anshuhan. Can you hear me?
Yes, I can hear
All
you.
right.
Go ahead.
All right. Thank you for the introduction. My name is Robert Fokenbak-Siro from Kenya, and I'm studying nuclear engineering and thermal physics. So I'm going to talk about the concept for the next generation nuclear reactors. This is what called generation 4. And I'm going to use the European sodium cool fast neutron reactor to demonstrate the concept. So far, Teta has talked about neutrons, reactors that are operating in the thermal spectrum. In most cases, we just have the division into two major categories. We have reactors operating the thermal spectrum and the ones operating on the fast spectrum, or the fast neutron spectrum, with an energy of about 1 to 20 mega electron volts. So this is a concept that is considered in what's called the Generation 4 International Forum, and it's crucial in the sense that it will enable us to allow what you call closing of the fuel cycle, and also utilization of nuclear fuel in the sense of fertile materials, and not necessarily subjecting these materials into what's called uranium enrichment and so forth. So that is briefly the main reason why this is a very significant concept in the nuclear arena. But of course, both thermal reactors and the fast reactors, they are all operating the same concept, what we call nuclear fission. Let's move on to the next slide, please. All right, so in the introduction bit, I'll briefly talk about what a fast neutron reactor is. and the concepts used in a fast neutron reactor, like what we call nuclear transmutation, and capture and fusion cross-sections, and then I'll give a few characteristics of the European sodium-cooled fast neutron reactor. Let's move on to the next slide, please. All right, so what is a fast neutron reactor? Like I said before, a fast neutron reactor is a reactor that operates on the fast neutron spectrum. That is neutrons with an energy of between 1 to 20 megaelectron volts. And what makes them special, as you had also indicated before, is the sense that we don't really have to subject the material that is used as the volumetric heat generation source to enrichment. In that sense, because normally the fuel materials that we use in nuclear, they come in two tests. There is what we call the fertile materials and the fissile materials. The fertile materials are the ones that are not really readily fissile in nature. So we have to subject them first to absorption. We have to use a neutron bullet. Then it absorbs the first neutron, and then it's subject to what we call transmutation. And then we end up with a fissile material, and the chain continues. So in that sense, we don't really need to subject this particular material into what we call enrichment process, which is also a very crucial stage in the entire nuclear cycle. So in a fast neutron reactor, as you can see on the diagram, we are using what we call a liquid metal as a coolant. And as you had seen before, in the thermal reactors, we use water, in most cases, both as a coolant and a moderator, like what you have in the VVER 1200 and all the VVER family and so forth. But in this case, sodium is used as a coolant. And why is sodium really special in this case? It's a special material for us in a fast reactor in the sense that it has a low absorption section, of course, and it has a high scattering cross-section. And also it has very impressive what we call thermophysical properties like thermal conductivity, isobaric specific heat capacity, and so forth. Those are really crucial. If you try to do the comparison with the coolant that you have in the thermal reactors, it gives us that capability to do more work in the fissile zone, as we'll see in the near. I mean, the next few slides, I think, maybe the next two slides, I think. So, all right, no, not yet. So in the case of nuclear transmutation, again, this is also a concept for fast reactors. Like I said, we don't really need to subject the fuel into what we call enrichment. So in nuclear transmutation, the fertile materials are applicable. The fertile material in this case is uranium-238, and of course, plutonium-238 is also a fertile material. So if it's a first reactor that is operating on what we call a MOX or mixed oxides, then we have both uranium dioxide and plutonium dioxide. So uranium-238, it absorbs a neutron, and then we end up with uranium-239, as you can see, and then it transitions between two beta minus decays all the way to plutonium-239, and then the plutonium-239 is a fissile material, so the fuel in the reactor. So all the red labels in this case represent fissile materials, and the green labels are fertile materials. So this is entirely what is happening within the fissile zone of a fast neutron reactor. So we don't really need to subject the volumetric heat generation source to enrichment. Let's move on to the next slide. All right, so there is also a concept called capture and fusion cross-sections when you're dealing with materials. Like I had mentioned before, the cross-section concept is very crucial if you are also choosing the moderator or any material that is in the fissile zone or the fissile volume of a nuclear reactor. So in the capture and fusion cross-section, from a mathematical point of view, if we talk about if you say that a material has a high capture cross-section, then it simply means there is a high probability of that particular material absorbing a neutron. But then the neutron doesn't facilitate what you call fission. So that would be an ideal characteristic of a material that is used as an absorber, or what you call the control and protection system, what is used in the CPS system, what you call control rods, and also what to use as a diverse shutdown devices, also in the concept of fast reactors. And of course, if we're talking about fusion cross-section, of course, in this case, this material absorbs the neutron, but then the neutron facilitates further fissioning process, or the splitting of this particular target nucleus. So all those are concepts that are very crucial for us in determining which materials are appropriate as moderators in a nuclear reactor, which ones are appropriate as coolants, and which ones are supposed to be used as in the control and protection system as diverse shutdown devices and control shutdown devices. So that is basically the concept of cross-sections as deployed also even in thermal reactors, by the way, and in fast neutron reactors. Next slide, please. All right, so these are some of the few characteristics of the European sodium-cooled fast reactor. By the way, this is it's not a reactor that is in operation. This is a design concept, and I didn't really find enough information about it, of course, because it's still in the design phase. So there's not so much information about it available in the public domain. But everything that is presented here is, of course, what is in the public domain. So this is also a pool type. As you had seen, the fissile zone is immersed in a pool of sodium as a coolant. And of course, there is no moderation in this case too. And the electrical output for this reactor is about 1,500 megawatts electric. And the thermal output, or what you get from the volumetric heat generation source, is 3,600 megawatt thermal. And sorry, there is someone talking. Oh, all right. So in the inlet and the outlet of this particular reactor, we have temperatures of about 395 and 545 degrees centigrade. And this is very crucial. As you can see, the range is too huge. If you try to compare this value to what we have in the case of PWRs, normally in the PWRs, this range is not supposed to go, I think it's between 20 and then 25 degrees centigrade. But in this case, you can see 545 minus 395 is about 150 degrees centigrade. So the water, the coolant gets heated to a temperature of 545. So the delta T in this case is 150. That's a very huge difference. And of course, like we had said before, the reason as to why that is the case is because sodium has very impressive thermophysical properties, very high isobaric specific heat capacity, and so forth. Next slide, please. All right, so in this preceding slides, briefly talk about the European sodium-cooled fast reactor concept. Show you what the axial view of the MOX core looks like, and the radial view of the MOX, and also we'll talk about the fuel subassembly and the CPS system. But I've not really, these are diagrams that I generated from the Monte Carlo code I prepared in Python. So they're not standard diagrams, yes, but they're good for explaining what is happening in the fissile zone for the first reactor. Next slide, please. All right, so this is what the axial view of the MOX core for the European sodium-cooled fast reactor looks like. It's for the axial view, we have two reflectors. There is a top reflectors and then the bottom axial reflectors. And I don't know if you can allow me to maybe be able to share my cursor on the screen from your end. Mm-hmm. Is it possible now? Can you see my cursor? Hello? Oh, all right, all right. Okay, so no, let's move on to the previous slide, please. All right, so in the axial view of the MOX core, something that is blocking my screen here. I don't know if it's my screen or the. I don't know if it's my screen. There's something that is blocking the screen. Okay, so in the axial view of the European sodium cooled fast reactor, this is the fissile zone, the fissile zone, and also the sections of the core constituting the reactor. This is the top, I mean, constituting the reflectors. These are the top axial reflectors. That is between the top axial reflectors are all the way from here to this particular region. And the bottom axial reflectors, of course, from here to here. So from here to here is about approximately 70 centimeters in height. And the bottom reflectors are approximately 30 centimeters in height. And the fissile zone is 1 meter or 100 centimeters. You can see from 50 to negative 150. This is where we have the fuel. The reflectors are here. And then there is what you call gas plenum between the top reflectors and the fissile height. There's a gas plenum which is approximately 11 centimeters in height. And then there is also a gas plenum in the fissile zone. There's a gas plenum down just after, immediately after the bottom reflectors, which are also represented by the orange color. And then, of course, in the central part, we have a subassembly that is also stuffed with the reflectors. What we call sodium is used as a reflector material, by the way, in this case. And between the inner fuel zone and the outer fuel zone, also for the axial view, you can see these brown, subassemblies. So this is a subassembly constituting what you call the CPS system, both the control and protection system known as the control shutdown device, and also what you call the diverse shutdown devices. And of course, towards the periphery here, we also have the radial reflectors. Now, these are not axial reflectors. These are radial reflectors, also subassemblies that are stuffed with solid sodium. All right, so that is the axial view. Basically, that is the axial view, and we'll talk much about the CPS system also in the preceding slides. But even before we go to that, this, for the case of the CPS system, both for the control, for the diverse shutdown devices and the control shutdown devices, we also have the absorber material. There's a height constituting the absorber material that is approximately 70 centimeters plus 11 centimeters. You can see here. And then the rest of the height for the CPS system constitutes what we call a follower material, a mixture of sodium and the ODS steel, proportions of about 8% and of course 92%. Next slide, please. All right, so in the next slide, this is now what we call the radial view of the MOX core. The radial view of the MOX core it reveals what we call the inner fuel zone, the outer fuel zone, and of course now you can see clearly how the radial reflectors look like for this concept. And this arrangement, as you can see, so many colors here. It's not really a fancy arrangement, or things are not really done in this sort of for fun. But then there's a scientific explanation. Someone who does neutronics will be able to explain that to you. So at the central part here, there's a subassembly stuffed with sodium, also acting as a radial reflector. And towards the periphery here, subassemblies constituting sodium again, also as radial reflectors. And then in the inner fuel zone, we have a MOX fuel now. Like you said, MOX fuel constitutes both plutonium dioxide and uranium dioxide, and they have a different enrichment levels. So there's a different enrichment level for uranium dioxide that is in the central zone, sorry, in the inner zone for the fuel, and then in the outer zone also there's a different enrichment for uranium dioxide. Sorry, uranium in the case of uranium dioxide, and the same is applicable for plutonium dioxide in both zones. And then the brown ones, so the brown subassemblies represent what's called the CPS system, also not just arranged in random, but then there is what we call the control shutdown devices, which are normally used in these control shutdown devices are normally used in normal operation of the reactor core, of the reactor. And the diverse shutdown devices are the ones that we use when we want to facilitate what we call emergency shutdown, or known as a scrum. So the control shutdown devices constitute about 18 subassemblies, no, 24 subassemblies actually. So there are 18 subassemblies at the boundaries between the outer fuel zone and the inner fuel zone. And then in the immediately after the reflectors, we also have a ring constituting again 6 subassemblies that are stuffed with absorber materials for the control shutdown devices. And in between the inner ring and the outer ring constitutes about 9 subassemblies also stuffed with absorber materials for the diverse shutdown devices. Now you can see also I included a code snippet here in this case, just giving the proportions for the materials that are used as fuel and even the structural materials in this case. I'll share, if you want detailed information on this or the materials and their proportions, you can email me. I think the email provided in the very last slide, so I can share this with you, not the code, but of course, just an information on the materials if you are interested in doing neutronic analysis and so forth. So as you can see, the proportions are also given here, and their percentage for the inner fuel zone, the outer fuel zone, and of course, the structural materials or the material that has been adopted as the wrapper for the subassemblies. And you can also see that the subassemblies in this design concept also resemble the subassemblies we know in the VVR 1200. They are hexagonal in shape. So the wrapper materials constitute EM 110 steel, which is also defined here. You can see about 89% iron and about 0.8% molybdenum and so forth. All these indicated just in the materials file. So let's move on to the next slide, please. All right, so this is now what the fuel looks like, the subassemblies constituting the fuel. The fuel material MOX is MOX, of course, constituting uranium dioxide and plutonium dioxide. And then the wrapper material also, as you can see, is ODS steel for the fuel. ODS steel also defined in this manner. You can see all the elements constituting the ODS steel in the exact proportions as they are also indicated here. And of course, for the EM steel, in this case, the EM steel is what is adopted also as an hexagonal wrapper material. The cladding material also for the fuel is ODS steel. The cladding material for the fuel is what is between because the fuels are organized in pellets, just like we know in thermal reactors. It's the exact same arrangement, except the material that has been adopted in the pellet is slightly different. So the ones we know, for instance, the VVR 1200, their proportions are a bit different for the case of MOX. But of course, if you try to do neutronic analysis with the exact geometries for the VVR 1200, and even thermohydraulic analysis of the same core, you'll realize that even in the VVR 1200, we can use the concept of MOX and so forth. So these are really just slight differences. And next slide, please. So in the next slide, this is what we have, what we now call the control and protection system. Like I said, they're divided into 2 categories. They are the ones that are used in normal operation of the reactor, and there are ones that are only used in situations where you want to subject the reactor into what we call emergency shutdown or scrum. So in this case, the first one here, this is what we now call the control shutdown device. The control shutdown device constitutes what boron carbide as the absorber material, is a material with a higher absorption cross-section. and of course very low scattering cross-section, because when you use in our CPS system, we don't want to use a material that has a high scattering cross-section. So this is boron carbide with about boron 10 enrichment in this material is about 20%, I think. So 20% enrichment. I think that is also indicated of course, it's indicated here, 19.9% enrichment in the boron 10. And then for the diverse shade and device, the enrichment for boron 10 is about 100%. So if it's 100%, of course, meaning that material has been subjected to enrichment. But this one, which is 20% in the boron carbide, this is just natural boron carbide. It's not really subjected to enrichment. So the composition of boron 10 in the case is 20%. But if it's subjected to enrichment, then we raise the level to about 90% in the boron carbide. So that is the main difference between the two of them. I mean, the diverse shutdown device and the control shutdown device. Let's move on to the diverse shutdown device, please. So in the diverse shutdown device, you can also see there's a difference in terms of the geometries. Of course, in the first one, in the control shutdown device, the subassemblies or the absorber materials are organized in a manner that they give us what's called the hexagonal trace. But in this case, you can see they're organized in a cylindrical way. Yes, someone who does neutronics will be able to explain to you how that is really crucial in a case where we want to create a difference between these two materials as far as the application in the reactor core is concerned. So like I said, the diverse shutdown devices are only deployed in situations where we want to subject this particular reactor to emergency shutdown. And that is all about the European sodium-cooled fast neutron reactor. It's a design concept, and this is also one of the reactors that will enable us facilitate the closing of the fuel cycle, which we really hope for. And of course, I think here in Russia, this concept is also, I mean, the first reactors in Russia that we know are the BN series. In the United States, again, they are developing fast reactors. The first flux facility. We also have the fast breeder reactor, and China is also working on a fast reactor. It's an experimental fast reactor. So the fast reactor concept is being developed in many countries, because there is where the future of nuclear fission is right now. We want to optimize on usage of raw materials. At the same time, we want to close the nuclear fuel cycle, and we also want to deploy what we call cost efficacy, or maximizing efficiency, but lowering the cost of our reactors, and also increasing what we call safety operations of our reactors. So that's all about the sodium-cooled fast neutron reactor. On the European sodium-cooled fast neutron reactor concept, which is a design concept. If you want to get more information about this, especially on the basis of the materials and the exact compositions, you can email me. I think the email is provided here, and I'll share the information with you. Thank you very much for your attention.
Thank you very much, Zero, for your wonderful presentation. So, dear audience, do you have any questions? Okay, in that case, there's no questions. So you can find us on social media platforms such as Facebook, Insta, VK, and YouTube. And this webinar will be uploaded to YouTube later. So thank you very much for your attention, and see you again in another webinar. Thank you. Goodbye.